Hi, everyone. Sometime next week, at a date still to be determined, I'm going to set up a network tournament for those of you who are interested in entering your machine players to battle in the network battle of the gods. So the instructions for how to enter your machine player into the tournament are linked from the home web page, or the class web page. I would like to encourage all of you to enter. Entering is not mandatory, it's not required, but if your machine player is working and you want to give it a shot, then please do. Even if you haven't put a lot of effort into it, you might get lucky, and the winners are going to get gift certificates to Amoeba Records. So you'll get a free CD out of it. And you are welcome to make additional changes to your machine player. It doesn't have to be the same as the one you submitted for Project 2. But in order to get it to work, you do have to make one change to your machine player so that it is in its own package that is named after your team. And so this adjustment will take about maybe 10 or 15 minutes for you to do. Once you've done this adjustment, the network program that you have can not only play your machine player against you or against itself, but you can play your machine player against other groups' machine players. So you can try that out too if you want, though, or you can just wait till the tournament and see how your machine player does against other people's machine players. And so I'll have the tournament sometime probably during the next week in the evening in 306 Soda whenever we can get it and whenever Len can be there to help run the tournament. And I'll remind you again about this regularly. Today's lecture is on amortized analysis. There have been a bunch of algorithms I've told you about during the semester where they have worst-case times that are different from the actual running time that you can expect in practice. So a lot of times I have told you that the average time of this or that algorithm is better than the worst-case time. And there are two different ways in which an algorithm can be better than its worst-case time. One is there are algorithms that have the occasional operation that's very slow, but most of the operations are much faster. And when you do a bunch of operations, you can always guarantee that the bunch of operations together will be run in a certain time, even though there might be the occasional slow operation. And the technique we use to analyze that is called amortized analysis, and that's the subject of today's lecture. And so these average time algorithms, where you know that the average time is absolutely positively guaranteed to be faster than the worst case time, are hash tables, disjoint sets, and splay trees. But there's also another fundamentally different notion of average time, where we have an algorithm that uses randomization to make itself faster, and where the expected running time, the average probabilistically expected running time, is faster than the worst case running time. And that's a different idea. That's analyzed by something called randomized analysis, which will be the subject of Friday's lecture. And the algorithms that fit in that mold are quicksort, quickselect, and hash tables again, because hash functions we try to model as random functions. So one of the purposes of these two lectures, Wednesday and Friday, is to help you try to get straight in your head what is the difference between amortized analysis and randomized analysis, and why there are two very different notions of what average time means. So the easiest way to do amortized analysis, but one that's not always applicable, is called the averaging method. And we can use the averaging method to analyze hash tables where you resize the hash table. And you know resizing a hash table can be a very expensive operation, but it doesn't happen very often. And if we only do insertions, the averaging method is enough to be able to analyze it. So here's how we look at it. Just to keep things simple, let's suppose that a newly created hash table has only one bucket. Now, obviously, this is stupid, and you wouldn't do it in practice, but it's actually the slowest case. So if you analyze this case and show that the average running time for hash table operations is big O of 1 in this case, then you're going to have the same result if you start with a hash table with 1,000 buckets or whatever you choose. So we're just going to pick the worst case and analyze that, and then it applies to all the cases. Now, we're going to assume that the chains do not grow longer than big O of 1. And I'll justify that assumption on Friday when we look at randomized analysis. And we're going to assume that any operation that doesn't resize the hash table takes order 1 time. And so it's only when we resize the table that we're going to have problems with the analysis. Let's go a little bit beyond saying it takes order 1 time. I want to work with actual numerical quantities of time here. So let's just say that it takes less than or equal to 1 second. Okay, actually 1 second is ridiculously slow these days, but I only care about the big O analysis today. Constant factors don't matter. So I'm just saying 1 second because it's faster than saying 1 microsecond. Now, a hash table has, recall we use big N for the number of buckets, and we use little n for the number of items. Now, suppose that the insert operation doubles the size of a hash table when little n and big N are equal just before I add the new item to the little n. Okay, so what I'm saying here is little n here does not count the new item yet. I've just called the insert method. I look at the hash table. There are already little n items in it and big N buckets, and those two numbers are equal before I count the new item. So I say I'm going to resize the hash table. So I'm going to double big N, twice as many buckets, and then I'm going to insert the new item, which means I'll increment little n by 1. So the purpose of this scheme is to make sure that the load factor never goes above 1. All right, and let's suppose this resizing operation takes at most 2n seconds. Where that's little n. So 2n seconds to create a new array of size 2n and rehash all of the old items from the old hash table into the new one. Now, when resizing is done, well, when we started, little n and big N were equal, but by the time we're done, big N will have doubled. We double the number of buckets. And that's before we insert the new item. Then we insert the new item, so little n increases by 1. So this is our model for how the hash table works. Now that we've got the model, let's analyze how long it takes to do I insertion operations starting from an empty hash table. And when we talk about amortized analysis, we almost always have this assumption that we're going to start with an empty data structure and look at the average time per operation from the very beginning. That way, if you start at an arbitrary time, you might start just before a super slow operation, like a hash table resizing. So to be fair, we should really want to look at the average time per operation starting from an empty data structure. So that's what we're going to do. We're going to construct an empty hash table. And we're going to perform insert operations. So when we're done doing insert operations, well, obviously the number of items in the table is I. And the number of buckets is, well, the number of buckets is based on the way we've set up this hash table. It's always going to be a power of 2. And it's never going to be smaller than little n, because we never allowed the load factor to exceed 1. So big N is basically the smallest factor of 2, smallest power of 2. That is greater than or equal to little n. And that's what things look like after we do these insert operations. Now, what I want to do is I want to look, what is the total time that all of these operations cost? Well, let's look just at the resizing operations. How much did those cost? Well, I start with a 1-bucket hash table. When I double it, I go up to 2 buckets. And according to my model, it costs 2 seconds to go from 1 bucket to 2 buckets. Then later on, I go from 2 buckets to 4 buckets, and that takes 4 seconds. Later on, I go to 8 buckets, and that takes 8 seconds. And so on until, well, whatever big N is when I'm done. The very last time I resize, it's going to take big N seconds, where big N is the number of buckets in the final hash table that I end up with when I'm done. And this is a geometric series, which I imagine some of you have encountered in math classes, and hopefully your TAs have talked about this, or they will. But that adds up to 2 big N minus 2. So you can see that the total time is big O of big N. So again, the cost of insert operations is less than or equal to, well, every insert costs a base cost of 1 second, not counting resizing. So that's I seconds for all of the work it does to insert an item into a hash table, except resizing. And then I add the cost of resizing on top of that. Well, how big can big N get? Well, I actually know a bound on big N in terms of little n. Basically, big N is the smallest power of 2 that's greater than or equal to little n. So it can't be bigger than twice little n. Actually, it's strictly less than twice little n. In the worst case, it might be 2n minus 1. And that's equal to 2I, where I is the number of insertion operations. And so the total cost, I plus 2 big N minus 2, that's in big O of, well, if I substitute in this upper bound on big N, then that's in big O of 5I minus 2. Or, since the constants don't really matter, that's just big O of I time to do insert operations. And that means that the average running time of an insert assuming that I take my average, starting from an empty hash table, is in big O of I divided by the number of insert operations I did, which is I. And that's the same as big O of 1. In other words, it took, on average, constant time per operation, even though some of the operations were very expensive. The fact that a few of the operations did a lot of resizing and were super expensive doesn't change the fact that the average time was still constant. So are there any questions about that? All right. So when you do an average in this particular way, another way of saying it is that the amortized running time, this is the formal way of saying it, is that the amortized running time of insert is in big O of 1, even though the worst case running time is in theta n. And what makes this different than randomized time is that a sequence of I inserts will always cost big O of time in the worst case, no matter what. Unlike, say, quicksort, which runs in n log n expected time, but could run in n squared in the worst case. With an amortized algorithm, you know that when you add up all the operations together, they will always run in big O of 1 average time, even if you had a few bad ones. Any questions on that? So averaging is nice and simple. The problem is it won't work for deletions. And the reason is if I allow a hash table to have both insert operations and delete operations, I could do any sequence of inserts and deletes. I could do 100 inserts and then 10 deletes and then 20 inserts and then 5 deletes and then alternate between inserts and deletes for a while, one at a time. And there's so many combinations that I can't look at every possible combination and average them all. So I need to do something more sophisticated if I want to be able to apply amortized analysis to a hash table that can delete, well, by delete I mean resize the table downward to smaller hash table, as well as resize it upwards to a bigger hash table. And so the method that does that is called the accounting method. So again, we're supposing now that the hash table can resize in both directions. Not only does it expand when it gets big to keep the load factor down and to keep the cost of operations down, but it also reduces itself in size if the load factor gets too small to save memory so that other applications will be able to use that memory instead. Now, let's re-examine our notion of time. I talked about operations taking 1 second. Of course, 1 second is really slow. So let me give you a new unit of time, which I will call $1. And when I talk about $1, I mean a unit of time which is just long enough to accommodate any one constant time operation that my algorithm does that I care about. So $1 is a very flexible unit of time. It expands to fit anything that I want to fit into it, as long as that anything takes constant time. So again, $, unit of time, to execute whatever is the slowest constant time computation that I will need for my algorithm. So now that I've got this dollar concept, I'm going to assign dollar costs to all my operations. I'm actually going to assign two different costs to each operation that my data structure can do. So each operation will have an amortized cost, and that is the number of dollars that we charge to do that operation. And there's also what's called the actual cost. And the actual cost is the actual number of constant time operations that the algorithm performs. Now, the idea here is that my actual costs are things that vary a lot. Like when you do an insert operation on a hash table, sometimes the actual cost is $1. Sometimes the actual cost is $1 million because you've just resized a 500,000 item hash table. So the actual cost can be really variable. And the purpose of an amortized cost is to sort of average out, smooth out costs over a large sequence of operations, so you can get a handle of what your average running times are for an operation and not be misled by a few rare slow operations that resize the hash table or where the display tree is completely unbalanced and you have to rebalance it. Now, let's look at one particular operation. So I do an operation and the actual cost turns out to be a particular amount. Like maybe it turns out to be $1, and maybe it turns out to be $1 million the next time. But the amortized cost of my operation is always going to be maybe $5, no matter what. Now, so sometimes the actual cost is greater than the amortized cost, but usually, hopefully, it's less than or equal to. So what does that mean? If the amortized cost is greater than the actual cost, like when our hash table does not resize itself, then we have extra dollars from this amortized cost that we're charging in our analysis. And we can actually take those extra dollars and save them in an imaginary bank and spend them on later operations. Of course, the reverse situation appears sometimes. Every once in a while, you resize the hash table, and the actual cost is bigger, maybe hugely bigger, than the amortized cost. And when that happens, that means you have to withdraw money from the bank to pay for your overcharge. Now, if the bank balance goes into surplus, that's good news because it means that the actual running time of our algorithm is less than what the amortized costs imply. On the other hand, if the reverse is true, if we go into debt and we owe the bank money, then our entire amortized analysis is wrong, and whatever we're claiming is the amortized cost, it just ain't true. So the rule here is never overdraw your account. Okay, so you might be wondering, what is all this nonsense about storing time in the bank? Well, think of it this way. What we're trying to do is we're trying to prove that the average running time for an operation is not bigger than, say, a constant. Here's another way we could do this. Suppose that your dad gives you an allowance of $500 a month. Good dad. So suppose that you only actually spend $100 a month of it, and you put the other $400 in the bank. If you do this for long enough, eventually you'll be able to save up and buy a $30,000 car. But the fact that you bought a $30,000 car doesn't change the fact that you're still only spending an average of $500 a month. So that's exactly what amortized analysis is. It's just the idea that if you save something up, then you can prove that you've only spent $500 a month despite having made a $1 million purchase after saving up long enough. So let's come back to the amortized analysis by the accounting method of hash tables. Now we're going to do it right. Not that we did it wrong before, but we were restricted in what we could do with the averaging method. The accounting method gives us more power. Every operation I'm going to say that since this is how hash tables work, every operation is going to take $1 of actual time When I say every operation, I mean the insert method, the remove method, and the find method. Those three methods, each of them is going to take $1 of actual time unless they resize the hash table. All right, so I claim that, no, I'm not there yet. Let's look at what our model for the hash table is. The insert method is going to work the same way as it did before when I talked about the averaging method. So insert says that it doubles the size if the load factor would be greater than 1 otherwise. So again, it's the same rule as before. If the load factor is not going to go over 1, I don't resize. But if adding the new item would push the load factor just over 1, it's time to resize and double the hash table. Remove is going to be roughly the reverse rule. Remove occasionally halves the size of the hash table, cuts it by a factor of 2. And it does that if the load factor would drop below 1/4. So I'm willing to live with a situation where there are 4 buckets for every 1 item in the hash table, but I'm not willing to go 1 item lower than that. As soon as I try to delete the item that would make little n less than 1/4 of big N, I immediately cut the hash table in half, rehash all the items, except for the one I'm deleting. All right, by trial and error, I came up with the following amortized costs. I'm going to say that insert costs $5. And remove, turns out it also costs $5. And the lucky find operation is only going to cost $1. Why does find cost $1? Because it never resizes the hash table. So find's the easy one. Now the big question is this accounting valid or will I go broke? So I want to prove that I'm not going to go broke, that the bank will never go into debt. I'll never owe the bank a penny, even for a second. To do that, let's consider the case where a hash table is new. Or has just been resized. Well, I claim that if this table has n buckets, big N buckets, right after I finish creating or resizing it, then at that moment, before I do any more operations, it has between big N over 2 minus 1 and big N over 2 plus 1 items. Where do I get this idea from? Well, you can check all three cases. So the three cases are this. If the table is new, then it has 1 bucket and 0 items. So in that case, this works out. Check. If the table has just been doubled, well, first I set big N to be twice little n, and then I increase little n by 1. So it has the result that little n is now big N over 2 plus 1 items. And if the hash table has just been cut in half, well, when I cut a hash table in half, it's because the hash table has 4 times as many buckets as items. After I cut it in half, it only has twice as many buckets as items, or in other words, it has half as many items as buckets. And then I subtract 1, getting n over 2 minus 1 items left after the deletion. So you can check that in each of these three cases, what I said about the number of items in the table is always correct. Any questions so far? All right. Well, so based on this, one of the things that's interesting about this scheme is that at any moment in time, you can just look at the hash table without knowing anything about the previous history of operations that were done to that hash table. You can just look at how many buckets there are and how many items there are and figure out a lower bound on how much cash must be in the bank. So even though you can't look at the past history, you can just look at a hash table and say, oh, well, that hash table must have at least $30 in the bank. And here's how you know. Well, basically, we know this. We know that right after a hash table is created or resized, there's this many items in it. And so if the hash table drifts outside of this range, away from having this many items, that tells me that there's cash in the bank. Because every time I take a step outside of this range, what am I doing? I'm either doing an insert or a remove that increases or reduces the number of items. And each insert or remove, I charge $5 for. The actual costs of those operations is just $1. So every time I move, every step I take away from this range puts $4 more in the bank. Let's see. So that's $4 I'm saving up with every insert and remove operation until I need to pay for a table resizing. Well, based on that formula, there must be at least 4 times how far little n has strayed from that range. Dollars saved in the bank. Again, you'll notice that this is a function only of the data structure as it exists at the current moment, and I don't have to know anything about the history of how we got to this state, whether we just did a remove or just did an insert operation, to figure out that there's this much money in the bank. And so this is going to be enough to pay for the resizing operations. So let's look at those. Let's do insert first. Every insert costs $1 actual dollar. Puts $4 in the bank. Only then, if there's a resizing operation, we're going to take that money right back out. But we only resize, and insert only resizes the table if little n after the insert, or adding the new item, reaches big N plus 1. Now, I can take this big N plus 1 and plug it into this formula, and that tells me that there are at least $2N in the bank. And I get that just out of that formula. And, well, the cost of resizing a hash table from n buckets to 2n that cost is $2N. And that's what I've got in the bank at the very minimum, so we can afford it. Now, after we do this resizing, we might have no money left in the bank, but we're back in this situation again, so we're going to have to do more insert and remove operations before we're going to have to pay for another resize. That's the insert operation. The remove operation is pretty much the same thing. Every remove costs $1 actual dollar, puts 4 in the bank. Unless we do a resize, in which case now we're going to take a little bit back out. Remove resizes the table. If little n drops to big N over 4 minus 1, including the newest remove operation, like counting the current item that we're removing. And if that's the case, then we can plug this number into that formula, and this time we get N dollars. And the cost of resizing a hash table from n buckets down to n over 2 buckets. Well, let's be generous and say that's $n. Well, we have $n in the bank. We can afford it. And the bottom line is that the bank balance never drops below 0. For any of the operations in this analysis, and therefore, I have established that these amortized times that I guessed are valid. And since these amortized times are valid, and they're all constants, that means that the amortized cost of each of these operations is in big O of 1 for all of them. Any questions about that? You guys are just remarkably silent today. Do you actually believe me? All right. Why does this work? It really comes down to the same argument I gave you before. If your dad gives you an allowance of $500 a month, and you start with an empty bank account, and you only spend $100 a month, and then you save up until you can buy a car, and then you buy a $30,000 car, well, it's kind of obvious that you have still not spent more than an average of $500 a month. And in this case, the $500 a month allowance is the amortized cost. The $100 you spend each month, or the $30,000 you spend in your lucky car month, those are the actual costs here. But though the actual costs vary, the amortized costs is still $500 a month. So another way to look at it is you can just do bookkeeping. You keep your total amortized costs in one column and your total actual costs in another column. And each month you enter your allowance on the left and the actual amount you spend on the right. And, you know, maybe a lot of the time you spend $5 on an operation. And if it's a find operation, that costs $1. But whatever. And you just keep this up month after month until at one point you decide to resize a hash table or buy a car. Pretty much the same thing. And so you keep doing this, and you add up your total every month and see what the actual amortized, actual amount you put in the bank, the actual amount you took out of the bank. And as long as the thing on the left is bigger or equal to the thing on the right at the end of every month, you know that your amortized costs really are an upper bound on the average cost of your monthly expenses or of your display tree operations. One final note, though, since the rule is that the amount on the left has to be greater than or equal to the amount on the right, that means that amortized analysis only gives you an upper bound. Or at least an amortized analysis, as I'm teaching it here, only tells you a big O bound on the average running time. The way I've taught it here and the way it's usually used, it never gives you a lower bound. So you don't generally get big omegas or big thetas out of this technique. You only get big O's. Any questions? All right, well, on Friday we will contrast this with randomized analysis, our other average time technique.